Hi everyone. So today we're going to talk about Newton's first and third laws. And you may be thinking, hey, where is the second one? Well, the second one comes later because these two first laws basically refer to things that are not accelerating, things that are either moving at a constant speed or are still. Whereas the second law tells us how the movement of something changes. So for the first part of forces, we will just focus on things that are not moving, what we say in equilibrium. The first thing we're going to talk about is Newton's first law. And as you may remember from last year or from 2 years ago, Newton's first law talks about a body that is, well, moving at a constant speed or still. So here's the idea. Imagine that you're in outer space, and it helps a lot to think about things in outer space, because when you think about things on Earth, there's all kinds of stuff like air and friction and sound and all these things that complicate the model unnecessarily. So if you want to really understand what is happening, the easiest thing is just to imagine that you're in space, and then your intuition will give you some answer that is much closer to the real laws than what your intuition would tell you when you are on Earth. And I will show you why in a while. So you are in space and you have this little ball. So let's just say you're in your rocket and you, throw this ball out the window. Now, hopefully your intuition tells you that this ball is just going to come out of the rocket and just move at a constant speed. Its speed is not going to change whatsoever, and if nothing stops it, this ball is just going to keep moving infinitely far. And now what I want you to think is, okay, well, this ball is moving at a constant speed, but there is nothing pushing it, right? There's no forces acting on it. This thing is in vacuum, so around it, there's nothing. There isn't a little guy pushing it this way, there isn't a little guy pushing it that way. So there are exactly no forces acting on this thing, but this thing is moving. And this is a very important insight that actually people took very long to have. We needed Galileo to figure this out. Because most people thought that if something's moving, there must be a force on it. Because it seems logical, right? If I look at a box on the floor, I'm like, well, if I don't push it, it's not going to move. Then when I stop pushing it, it stops moving. So you would think, well, this means that if I want something to move, I need to do some kind of force on it. But this is not true, because if you go to outer space and you leave something to its own devices, it's just going to keep moving at a constant speed when there's no forces acting on it. And this leads us to the first version of Newton's first law, which is that when there's no forces acting on something, then this something is moving at a constant speed in a straight line. So no forces implies constant speed. Cool. Constant speed and straight line. Because of course, we don't expect this thing to start turning all of a sudden. If it started turning all of a sudden, started doing this, we would be very, very surprised, right? So we would assume that somebody is pushing this to the side. So no forces, constant speed, straight line. Now, of course, if I'm in outer space and I see something that's moving at a constant speed in a straight line, I may wonder, are there any forces acting on it? And it turns out that, well, probably not, because this thing is traveling in a straight line. If there were some forces acting on it, this thing would actually be changing its movement, and it's not. So we can actually change this law and make it go both ways. Right? So if there's no forces, then the thing is moving at a constant speed. But if the thing is moving at a constant speed, then there have to be no forces. Turns out, though, that this formulation is incorrect. We would be wrong to believe this. And let me show you why. So imagine that I'm still in outer space. I still have the same ball. Let me just maybe move this elsewhere. Okay. But now, next to my ball, there's two guys. Okay, there's this guy, number one. And, I mean, really doesn't make a lot of sense to think that these people can do forces in space because they have nothing to cling to. But let's just imagine for a moment that, you know, we have Superman and he can propulse himself somehow. So let's just make a cape, Superman this way, and there's a Superman clone on the other side. So here's my Superman clone. And yes, I did fail art when I was in high school. So we have Superman and the Superman clone. And this ball was moving at a constant speed this way. And now the Superman starts pushing it backwards because it's trying to stop the ball. So let's just represent this with this little arrow. And let's get used to this. When we represent the force, we always represent it as it's coming out from the center of the body, because we're really imagining that this body is infinitely small and contained in the very center. And now it turns out that the Superman clone is also pushing, but actually is trying to make it go faster, so it's pushing the other way. And because they're both the same person, because they're clones, they're pushing with exactly the same force. So what's going to happen? Well, if they're pushing with exactly the same force, then neither of them can win. Therefore, the movement of this thing is not going to change. It's not going to stop because the guy that's trying to stop it is not doing enough force to compensate for the other guy, but it's also not going to get any faster because there's a guy that's trying to stop it. So we see that having two guys pushing in opposite directions has exactly the same effect as having no person pushing in any direction. So we have two different situations that both give us the same answer. One possibility is no forces, and then we have movement at a constant speed in a straight line, but we also have that if the total force is zero, then we also have movement in a straight line, constant speed. So this leads us to the definitive statement of Newton's first law, which basically says that where there is no net force, and net force means just the total force, so when we add up all the forces, this implies straight line, constant speed. And now, if I see a ball that is moving in a straight line at a constant speed, I am allowed to think, well, either there is no net force, either there is no force, or the total force is zero. Therefore, there is no net force. So this thing goes both ways. So anything that's moving in a straight line, constant speed, has no net forces acting on it. And everybody seems to understand this perfectly well until you actually see some specific examples on Earth, and then suddenly people stop understanding. And we will see that in a couple of slides. But before we go into examples of the first law, I want to talk about something called the third law, which we also did when we were in the IGCSE. And the reason that I want to do this is because the two laws combined can explain most of what we see in our everyday lives. So I'm going to start with a very simple example, which is me jumping. So here's the floor. Here's me. So first time, bending my knees. And then I do a force down on the ground. And then, after that, I'm up in the air. And then, well, what's going on? Because last time I checked, when you jump, you're not pushing up. You're actually pushing down. You're pushing down on the floor. So if you're pushing down on the floor and not pushing yourself up, like in a pull-up, then why on earth are you actually going up? Seems pretty counterintuitive, right? So of course, what could be pushing me up? Well, it can't be me pushing myself up, because as I said, I'm pushing down and there is nothing over me where I can grab onto. So I'm not the one pushing up. And there's really only two things here. There's me and there's the ground. So the only other option is that it's the ground pushing me up. But why on earth would the ground push me up? Well, and the answer to this is called Newton's third law. And nowadays, I think that we would consider Newton's third law maybe more a consequence of something called momentum conservation, even though here we will learn momentum conservation as a consequence of Newton's third law. But yeah, the basic idea is that somehow, when I push down on the floor responds by pushing me up. Now, exactly with what force does the ground push me up? That's what we want to know. And in order to know this, it helps to look at the case where I'm just standing up. Now, when I'm standing up, my movement is not changing. I'm not being accelerated, and I'm moving in a straight line in the sense that, well, as straight as just being still is, right? So I'm still. My speed is constant. It's 0. And therefore, according to Newton's first law, this means that the net force acting on me has to be 0. Now, which force is acting on me? Well, there's two forces acting on me. One of them is the weight. And the weight, remember, the weight is a force which we calculate by multiplying my mass times the acceleration of gravity. And remember, the name of this force is the weight, not gravity, the weight. When we talk about gravity, we normally talk about the acceleration of gravity or the gravitational field strength, which is a different thing. Okay, so here's my weight that's pushing me down. Then something else has to be pushing me up, because otherwise I would be just falling through the floor. Well, what can be pushing me up? Well, it has to be the floor, right? So the floor must be pushing me up. With how much force? Well, if the floor was doing less force than my weight, then my weight would win. And if my weight won, then I would just go down. But that's not happening, right? Now, if the force was doing more force than my weight, then the floor would win, and then I would be going up. But that's also not happening, because I'm still on the floor. Therefore, the force that the floor does has to be exactly equal to my weight. We're going to call this the reaction force of the floor. And later on, we will give a physical explanation for why this happens. But this is the basic idea. Now, so it would look like this force that the floor does has to be equal to my weight. But that's actually also not true. Because when I jump, these two things are not equal anymore, right? When I jump, I'm going up. Which means that the force that the floor is doing to me has to be bigger than my weight. Because if it was smaller or equal to my weight, then I wouldn't be going up. So somehow I managed to get the reaction force from the floor bigger than my weight. How do I manage that? And hopefully, if you've ever jumped, you know that you manage this by pushing on the floor. So what you're doing is, on top of your weight, you're adding one more force, which is that of your legs pushing on the floor. So it seems like this reaction force is not really reacting to your weight. It's actually reacting to your push on the floor. So here, because of your weight, you are pushing down on the floor exactly with your weight. And then the floor is reacting with its reaction force, which is exactly equal to your weight. Then what happens is, when you want to jump, what you do is you increase the force with which you push the floor, making it bigger to your weight. And then because it's bigger to your weight, the floor reacts with exactly this force, overcoming your weight and then allowing you to jump. So this tells us basically that when I do a force on something, so for example, I am doing a force on the floor, then that something reacts by doing exactly the same force to me, but in the opposite direction. And this is Newton's third law, which we can express in a little drawing. So imagine that I have two bodies, A and B. Now what happens is that A, for example, does a force on B. And let's call force that A does to B. Well, when this happens, then body B will do exactly the same force but with opposite sign to A. So here we'll have the force that B does to A. Now, what's very important to understand is that these two forces are on different bodies. So they're not canceling each other out. Forces only cancel each other out if they are on the same body, right? If two people are pushing you in opposite directions, then you're not going to move. But if you're pushing one guy and that guy is pushing you, then you both are going to move because the forces are on different bodies and therefore they're not going to cancel out. And that's what people sometimes struggle to understand. So this does not preclude movement because the forces are on different bodies. A does a force to B, and then B reacts by doing a force to A. That's why when you shoot, you feel a recoil from a gun. Because you are doing a force to the bullet, and the bullet is doing a force to you. The bullet is going forward. So let me just show you. This is you. This is your gun. Right? Then the bullet feels a really big force for it because it's a very small bullet and goes really fast this way. Now you're way bigger than the bullet, so of course you feel the same force that the bullet feels, but of course you're much smaller than the bullet, and therefore you only feel a little recoil. You don't just jump that way. But the force is the same, it's just that the effect is not the same because the bullet's tiny and you're not. Okay, so now that we've talked about Newton's first and third laws, we are in a position to start talking about types of forces and exactly why they work the way they work. The first thing that we need to know is that the units of force are the newtons, and you should know this already. And 1 Newton is not a fundamental unit, it's a compound unit, and it's equal to 1 kilogram meter second to the minus 2. And remember that second to the minus 2 just means divided by second squared. But in the IB we like to have everything in one line, so we just use negative exponents. And when we do Newton's second law, why this is so will be very clear. Now, of course, you should already be familiar with some forces that we did in the IGCSE, for example, the weight, right? So if we have a ball that has mass m, it gets pulled down by the gravitational field with a force called the weight, which is equal to the mass times the gravitational field strength, sometimes called the gravitational acceleration, which on the surface of the Earth is equal to 10 meters per second squared. During this course, we will also talk about the gravitational acceleration at other points, like in space, and you'll see how this actually changes everywhere. But for usual stuff around you, this is always 10 meters per second squared. Another type of force that you've seen before is the force of the spring, which we normally call a tension, even though normally when we talk about tension we talk more about strings than springs. But remember that when you had a spring, so here's a spring, if I leave it be, it just stays like that, right? But if I want to make it bigger, to extend it a little bit by, let's say, a certain amount, let's just call this increase in x. Remember that this little delta thing is part of the x. So this whole thing means increase in x. It's not two different things, it's one thing. So every time that you see this thing, just read increase in whatever comes afterwards. Okay, so if I pull this by some amount increase in x, now the more that I pull, the more force I need to do to keep it there. And then I receive a force from the spring that's trying to restore it to its initial position, and this force is equal to something called the spring constant times the increase in x. Now, the beauty of this thing is that I can model the spring through the spring constant. So what this tells me is how strong the spring is. If I modify this very little, so if I make this, just put it a little bit this way, but I feel a huge force, this means that this K is very big, then this means that my spring is very stiff. And if on the other hand I need to extend the spring a lot, before I can feel some measurable force, it means that this must be very small, therefore the spring is very weak. So this K thing here tells me the strength of the spring. We can even figure out the units of this K thing just by remembering that units have to be consistent. So here I have newtons, right? Here I have newtons. Here I have some units that I don't know, so just call it units of k, and remember that this little bracket thingies means units of. So units of k times the units of x. What are the units of x? Well, if you know anything about anything, you will know that these are meters. So now this is just like an equation. Whatever is here times meters has to be equal to newtons. So therefore, the units of k have to be equal to newtons divided by meter, or newtons meter minus 1. So this tells you how many newtons of force do I get for every meter that I extend this spring. Sometimes we get this in centimeters because, of course, most springs are extended centimeters, not meters, so this is like pointless unit. But in SI units, that's the unit for K. So this is a classical example of force. This is the spring force, and this law here is called Hooke's law, which, again, you should know from the IGCSE. We can also compress the spring, again, by some amount increase of X, and the force is given by exactly the same thing. Later on we will see that there's actually a minus sign here, and this minus sign here corresponds to the fact that the force is always against whatever you're doing to the spring. But this is now not important. In magnitude, or like how big the force is just k times increment of x. One force that we're going to be seeing a lot during this course is the tension, but not of a spring, but of a string. So imagine that I have a string here, and here's one person, and here's another person, and we're both pulling the string. Okay, so we're both pulling the string with a certain force F. Now, what is happening here? Well, of course, this spring is made of billions and billions and billions of atoms that are connected together. They're really like little springs that do not want to be separated. So, of course, when I pull the string, the string reacts against being pulled by pushing exactly the opposite way. Now, imagine that here's my string, here's these two people, and we are at a stalemate, which means that this is not moving. We're both pulling, the string is not moving. So we are both pulling with a force F, and neither of the three is moving. Now I can imagine the string as just a bunch of atoms linked together somehow. Right? So here's a bunch of atoms, they're glued together, and then, so this guy here is feeling a force from me, F. But this guy's not moving, which means that there has to be some other force that's exactly equal to this force that I'm doing to it, going in the opposite direction. Now, how much force does this guy have to be feeling? Well, of course, F by going the other way, right? And who's doing this force? Well, it has to be this guy here, right? Because nobody else can be doing it. Nobody else is touching this guy. I'm touching this atom here, and then this other atom is touching this one. So this atom must be pulling this guy that way. And we're going to assume that all these atoms are, like, their mass is really, really small compared to me. Okay, so then, because this guy is pulling this guy with a force F, because of action and reaction, this guy must be pulling this guy with a force F the other way. So I'm going to draw that force F going this way. So this guy is being pulled with the force F this way, but it's also not moving, because the string is not moving. Therefore, something must be pulling it the other way, and guess what it is? Well, of course, it's the next guy, right? So you can see that then we have this force F that gets transmitted to this guy, because this is still the same force F, gets transmitted to the next guy, to the next guy, to the next guy, to the next guy, and each one of these guys will feel a force F this way and a force F that way, and will transmit that force to the next guy, and so on until it reaches here. So somehow this string is transmitting the force that I am doing, which is a remarkable property. That's why you can play games with strings, right? When I pull this way, then this guy immediately feels the pull, pulling it this way. But I'm not pulling him, it's the string that's pulling him. Because I'm not touching this guy, the string is touching this guy. So somehow my force gets communicated to the string, and it gets communicated to the string because of Newton's third law. The force that I do on this atom then gets a reaction, well, then this atom needs to be pulled by the next atom, and then because of action and reaction, we have these pairs of forces that get created in every atom until the force gets transmitted to the last one, and then poof, the force is transmitted to this guy here. Okay, now the force that the string does the opposite side, so I'm pushing it this way, but the string does not want to break, right? The string is being glued, so these atoms are pulling this guy in this way. Well, we call this force the tension of the string. And as you can see, because of what I just showed you, that these forces get communicated across each other, and because when there's no movement, these two forces have to equilibrate, then this tension here has to be exactly the same as the tension that this atom is doing, but the other way. And this is a very important result that will help us solve many, many, many problems when we're doing equilibrium and also non-equilibrium. So when I push a string on one end, it will resist with a tension, and on the other end there will be exactly the same tension but pointing the opposite way. Okay, now that we know about Newton's third law and we know about Newton's first law, we can start talking about something called normal reaction forces that I've briefly mentioned, but now we're going to do this a little better. So imagine that I have a box here with a certain mass m, and this box is standing here, and as I told you, there's a force on this box, which is the weight, which is equal to mg. So the weight is equal to the mass times gravity. But the box is not going down. And this means that something else is doing a force on the box. And of course, there's nothing here that could possibly do a force on the box, except for the ground. So therefore, this ground has to be pushing the box with a force that's equal to mg. And we call this force the normal reaction force. And we normally write it with an r. Some people write like n, well, it depends on who you ask, but we will normally use r. And well, we ask ourselves, we know that people can do forces, we know that animals can do forces, but how can something like the floor do a force, right? Like the floor is not moving, it's not doing anything, it's not an animated thing, so how can it be pushing anything up? So, yeah, we know this happens, but it is very hard to imagine why this would happen. And the way to imagine this is to remember that the floor is actually not something that's just rigid, but is actually made of atoms, right? And these atoms are placed next to each other, something like this, right? Normally in lattices, like in a crystal, something like that, right? And there's actually forces between those atoms, because these atoms, remember, are made of a plus nucleus and some electrons that are going around. And of course, when they're very far away, the total charge is 0, so they don't really influence each other. And so here I have my two atoms. But if I want to bring these two atoms together, then of course the repulsion between these two electrons starts being important, because these two are closer than the nuclei are. So these guys will start to repel each other, and it will get harder and harder and harder to bring these two guys together. So this is kind of like a spring, right? So it's like there's this spring between these two atoms. When they're far enough, nothing happens. But when I try to compress this spring enough, then this spring starts to complain. And if I put these guys close enough, then there will be a moment when I will have to push really, really, really hard if I want to get them any closer. Actually, if I want to get them completely close, theoretically, I would have to push infinitely hard. So, of course, when I put something on the floor, what this thing does is it's really pushing on these atoms. It's pushing down on these atoms, right? And therefore, these atoms are getting closer to the next atoms. And at the beginning, nothing happens. But as they get closer, the springs between them start to complain. They're like, hey, sorry, but that's too close. And they remember that when we have a spring, and the distances get smaller and smaller, then it responds with a force up. and this is what causes the reaction force. So I can just draw this in a little bit nicer. So here's my atoms, right? Here's my box, and then what the box does is it's really pushing my atoms down, and then these atoms were happily here, but these ones of course got pushed down, and then this spring here is compressed, so it's doing a force up, and we call the added force of all the atomic springs the normal reaction force. So that's what's really happening at a microscopic level, or at least that's a good model for what's happening at a microscopic level. Of course, things are always more complicated than this, but this model kind of works. Now, some people think mistakenly that reaction forces are always equal to the weight, and that's not true at all. I mean, of course, they're equal to the weight if I have something that's on a flat surface and nothing's happening to it, and the only force pushing down on here is the weight. But what if, for example, I have a box? So here's my floor, here's my box, but I am here, and I'm doing a little force lifting this up. Then this guy is not pushing as hard down on the floor, and therefore the floor doesn't have to react as much. So in this case, the normal reaction would be a little smaller than the weight. And there's other examples that we will actually see all the time in this course. So what if I have something like this? So here's my slope, and here's my box. Now in this case, the force of gravity, so the weight, points down. But the force is a vector. And what does this mean? Well, because it's a vector, it has components, right? So part of this force points this way, part of this force points this way. So now I can actually express this as a vector. So let's do this. And I say, well, there's a component that's perpendicular to the floor. Let's call this Wy. And there's a component that's actually horizontal to the floor, parallel to the floor, and I'm going to call this Wx. And this component here has nothing to do with the reaction, because this component here is what's pushing the box down. So only this component is actually going against the floor, and therefore the reaction force will only be equal to Wy in magnitude, but it will not be equal to the whole weight, which is mg. So it's very important in each case, in order to find the reaction force, I need to think, okay, well, what part, like how much force is really acting on the floor? Is it the whole weight? Is it just part of the weight? If something is like this, and there's a box here, now the box is falling this way, then there's absolutely no reaction force because nothing is pushing the wall. Now it's a wall. It was a ground. Now if you think about it, a wall is just a ground that's 90 degrees. Wow, that's deep. Okay, so basic idea, reaction force is always equal to the component of the weight that's pointing perpendicular to the floor, but not necessarily to the weight. And it's very important that you remember that forces are vectors, and therefore it's very important to know how to decompose this thing into vectors. And later on we will do an example of a calculation, and you will see me doing this so that at least you've seen it done once. Now, two of the most important types of forces that you will ever see in this course are drag forces and friction. And all I'm going to say about drag forces is that they're just forces that go against your movement. So for example, if I have a car and it's going this way, it's going to feel a drag force from the air, from the wind, really. And this drag force is actually proportional to the speed. So the faster I go, the more drag force that I feel. And we call this, and we will see this over and over again. But what I want to talk about now is actually friction. And friction is not with air. With air, it's just drag or air resistance. Friction is a force that's related to the contact between two surfaces. So imagine, again, my box. I always have a box. I have lots of boxes. So here's my box, a certain mass m, and it's moving this way with a certain speed. And we all know that eventually it's going to stop. And remember, if there were no forces acting on this guy would just keep going on forever. Just imagine it in space. So if it's stopping, it's because there has to be some force that's stopping it. And this force is friction. Now, what causes friction? Well, of course, it's the ground that causes friction, because if I did this in an ice field, this would just keep going, or at least it would keep going for a lot longer than if I do it in gravel, right? So it seems to be that there's a force of contact between the box and the floor that causes this to slow down, and we call this force friction. Sometimes FF, as in force of friction. Now what happens with the force of friction, we can again imagine that we zoom this in. So we take this part and we zoom it in. And then we will get something like this, right? The floor is not really smooth, but it's full of little cracks. And neither is the box. It's also not smooth. So of course when these two things get together, there will be forces that will not let them move against each other. We call this the addition of all those forces. That's the friction. So what does the friction depend on? Well, of course it depends on the material. So each material will have different friction with other materials. And in order to model this, we just basically try and we make tables with materials and how much friction they have with each other. But it depends on something else. So for example, if I have a box and that's being stopped, if I sit on it, so here's me sitting on it, what's going to happen is that it's going to stop much faster. Why? Well, because this thing is going to be cramped into there, and therefore it's going to be much harder to move. So it looks like the more interaction between this and these surfaces, the more friction there is. And what force describes the interaction between these two surfaces? Well, it's the force that we just talked about. It's the reaction force. So it turns out that the force of friction is proportional to the reaction force, to the normal reaction force between the box and the floor. So in mathematical terms, we can write this down. We can say that the force of friction is equal to something, some constant, because that's why it's proportional, times the reaction force R. Now, this constant, we call it the friction coefficient, and we write it with the Greek letter mu. Okay, that was a pretty crappy drawing, but that's the idea. That's how it looks like. It's like a U with a little extra stick here. So we call this the friction coefficient. Friction. And the good news is that you don't really have to calculate the friction coefficient. They will give it to you. Why? Because the only way to get this guy is by actually doing an experiment. So I get two surfaces. If I know the reaction force, I can calculate the friction force simply by, for example, pulling it. And when I know the friction force, then I can calculate this, and then I can write it on a table. And then the next guy doesn't have to do the experiment because I did it for him. But there's a subtlety for this thing. There's actually two friction coefficients. There's one we call the static friction coefficient. Static means no movement. And one that we call the dynamic friction coefficient. Dynamic just means that there's movement. Why do we need two for these guys? Well, because what if the box is already moving, then of course there will be more space between this and this, right? There will be like a layer of air between these two because of the movement of this box. So we would expect this thing to suffer less friction than when it's still on the floor. And actually, you guys, I'm sure that you've seen this. When you try to move a wardrobe, for example, when you start to push it, it's really, really hard. And then the moment it starts moving, you're like, whoa! Because you're still doing the force that you needed for the static friction coefficient. And the moment it's moving, it needs a lot less force. And it's really hard to control and to stop the force on time. So normally, this one is way smaller than this one. But they are both smaller than zero, because you can never have a frictional force that's bigger than the reaction force between these two. So a typical friction coefficient will be around, let's just say 0.2, 0.1, depending on the surface. Okay, now I'm going to show you an example calculation, but I'm going to do it without a single number, because this is something that you will get proficient as we move through the course, but using numbers is always a bad idea until the very, very end. Every time that you plug in something in your calculator, experience show that you have a 20% possibility, and I'm underestimated the possibility of making a mistake. So the more things that you put in your calculator, the more steps that you do in your calculator, the more likely you are to get something wrong. That's the first thing. And the second thing is that if you use only letters to do your calculations, you will find out that a lot of the things that you think you need, you actually don't need. And this happens, for example, a lot when you talk about kinetic energy and potential energy, where, for example, the masses 90% of the time cancel out. So I'm going to do a sample calculation only using letters, so that you can see the type of problem that you can be asked to do, and then of course you can do it with numbers. So imagine that I have, this is a slope, here I have a box of mass m. Let's say that I know this mass m, I just don't want to put in a number. And I also know the static friction coefficient. And what I ask myself is, what is the maximum angle at which I can put this thing before it starts sliding down? And you can actually calculate this, and you can actually find a formula that works for any m, which is the beauty of using letters. You do it once, and then you only need to plug in the numbers the next time you do the problem. Okay, so how do I do this? Well, the first thing that I do is I use something called a free body diagram. And the idea of a free body diagram is just thinking, okay, well, which body am I interested in? What's the body that moves and receives the forces? Well, obviously this guy here, the box, because the slope is not going to move. So this is my free body. Now, normally I will assume that the body is a point particle that is located in its center of mass. So all the forces act on its center of mass. However, the IB, for some reason that I still cannot understand, likes you to depict the forces of friction along the surface between the two things. Mainly, I guess that they do this because they think that friction acts along the surface. I think it's a really terrible idea, because when you have forces acting in different places, what you get is a rotation. But that's what the IB wants us to do, so that's how I'm going to draw this, even though, well, that's my formal protest in a YouTube video. Anyway, so here's my mass. And what I need to think about now is, okay, so what forces are acting on this guy? Well, the first one that I can think of is, of course, the weight. So there's going to be the weight. So here's my center of mass, and this is going to be pulled down by the weight, W. And just get used to writing W, because it's the weight. It's not G, it's not M, it's the weight. And I'm just going to remind myself that I can calculate this simply by multiplying M and G. What other forces are acting on this guy? Well, this is on a surface, so there has to be a reaction force acting on this guy. Now, in which direction is the reaction force going to act? Well, here's a clue: not this way, because the reaction force is always perpendicular to the surface, so it has to be acting this way. So let's just draw my reaction force. That's the second force that acts on this guy. Are there any other forces? Well, yes, there are, because there's friction acting on this guy. And friction will act against movement. In this case, the guy's not moving, but it's trying to move, or it's being pushed by gravity this way, right? Because gravity is pointing this way, and part of it is pointing this way. So friction will always oppose this motion, therefore it's going to point this way. So here's my friction that I'm going to draw, let's see, with this color. So my force of friction is going to go this way. And now I have a problem, right? Because there's two possible ways that this guy could move. One is this way, and of course he could also be moving this way. So there's two axes to this problem, and I need to solve this problem using both axes. Now, what I do when I have a problem with vectors, the first thing that I do is I need to always reduce it to these two directions. And which directions do I choose? Well, I could do it in any direction, but I choose the ones that are the easiest to work with. And in this case, it's clear that using this as my x-axis and this as my y-axis is the wisest choice. Because this will tell me kind of the vertical motion, and this will tell me about the horizontal motion. It's not really horizontal, it's tilted, but you see what I mean. Now this one is already along my y-axis, so I'm happy. I don't have to do anything. And this one is already around my x-axis, so I'm also happy. I don't have to do anything. But this one here is a pain, because it's pointing along both, right? There's part of this guy that's going this way, part of this guy that's going this way. So I have no choice but to take the component of this vector, to find the component that's pointing this way and the component that's pointing this way. So let's do this. Now remember, if this were a triangle, this is the hypotenuse. So if you're doing something where this is not the biggest part, you're doing it wrong. So what I need to do is I project this thing into both axes. So here I have my x-axis, here I have my y-axis, and I need to project this thing. So I take like a shadow of this thing against these axes. In this case, so first the x-axis, and here's the x component of my weight. I'm going to call it the wx. So this guy here is wx. It's the x component of my weight. And then on the other side, I'm going to take the other component, which is the projection along the y-axis. So this guy is going down, and it's just the part of this guy that is parallel to this axis here. Now, of course, all this depends on this angle, theta. So how do I get this component if I know this angle theta? Well, it takes a little while to see, but basically, of course, we need to use cosines and sines like we always do when we try to get components. And in order to do this, you can't just mindlessly think, oh, x cosine, y sine. You need to stop and think, what angles are we talking about? So this angle theta, in this triangle, where is it? And something tells me that it is in here, but I need to convince myself that this is so. So let's take a look. Okay, this is theta, and this is 90 degrees. So if this is 90 degrees, this plus this have to be 90 degrees. So this angle here. But I can just continue this thing here. So if this plus this are 90 degrees, and this is 90 degrees, then this thing here has to be equal to this thing here. So indeed, this angle here is theta. If you did not follow this, what I would say to you is get a piece of paper, draw it, and convince yourself that this is so. And I will make you do this when I see you in class. So please go ahead and do it. Okay, so anyway, here's my angle theta, and I want to calculate which part of my weight is going this way. So let's do this. So I have the y component of my weight will be the hypotenuse times the cosine, because it's the contiguous side, right? So there you go. So remember, opposite is sine, and this adjacent is cosine. So times the cosine of theta. And as a bonus, I also have wx, because if this one's the cosine, the other one has to be the sine. So my wx is the sine of theta. So it's the opposite of what you would expect, and the reason that it's the opposite that you would expect is because this angle goes here. So be very careful with this, it's really easy to get confused. Okay, so now I have all my forces, and now I can start calculating things. So let's do that. So the first thing that I would like to do is, well, in order to know whether this thing is going to move or not, well, I know that it's not going to start jumping or go into here. So what I'm really interested in is in the motion along this axis, the x-axis. And in order for this guy to stay still, what has to happen is that the friction force has to be equal to the x component of the weight, because these are the only two forces acting on my box in this direction. So what has to happen then is that the force of friction has to be equal to the x component of the weight. Now, the force of friction, though, remember, is the friction coefficient that I have times the reaction force. So I can replace this by friction coefficient times reaction force, and this has to be equal to the x component of the weight. Do I have the reaction force? Well, it turns out that I do, because in this direction there's only two forces acting on my box. There's the y component of the weight and the reaction force. And since this thing is not jumping up or going into my slope, these two things have to be equal, which means that the reaction force has to have the same magnitude, so it has to be just as big as the y component of the weight, which is this. So I can replace this by this. Good, so let's do it. So then from here, I'm like, well, static friction coefficient times the weight times the cosine of theta, and that's the x component of the weight. And how much is the x component of the weight? Well, I already calculated it. It's this much. Good. And now look at this beauty. Here is my weight. Here is my weight. Both are multiplying in each side, so I can just divide this equation by the weight, divide this by the weight, and remember, if I do the same thing on both sides, everything works out and the weight gets cancelled out. Wow, ain't that pretty? So then what I have is that the friction coefficient times the cosine of theta equals sine of theta. That's amazing. So we just discovered that the angle that will prevent this from going down has absolutely nothing to do with how heavy the box is. And we've done this by being smart enough not to plug in any numbers. So this tells you how important it is to not plug in the numbers until the end, because look at this. We didn't have to know the mass. We would have spent so much time plugging stuff into the calculator that we just didn't need at all. This is a very simple relationship. Now I can just solve this for theta. How do I do this? Well, let's do this. Well, the first thing that I need to realize is that if this equals this, then this equals this. So I can just write this as sine theta equals friction coefficient times the cosine of theta. And I'm going to do something that may look silly, but is actually very practical. Sine theta over cosine theta, and I'm also going to divide this by cosine theta. And of course here the cosine theta is going to cancel out. And now I'm like, what is sine theta divided by cosine theta? And hopefully you know this, but let me just show you what it is. Here I have a triangle. Here's theta. This is A, this is B, and this is H. Now, I know that the sine of theta, by definition, is this side over H. So it's A over H. I also know that the cosine theta, sorry, I forgot the theta here, is by definition this over this. So B over H. And I also know that the tangent of theta is also by definition, because that's how we define the tangent, is A over B. Good. Let's see what happens when I divide the sine over the cosine. So sine theta divided by cosine theta, that's A over H divided by B over H. Remember, division is nothing but multiplying by the inverse, which means A over H multiplied by this guy flipped. So H over B. And what happens to the H? Oh, it goes. So we have A over B, which is just the tangent of theta. So the sine of theta is, well, sine theta over cosine theta is nothing but the tangent of theta. I don't know if you knew this, but if you did know, now you know why this is so. Okay, so then all I need to do then, from here, tangent of theta equals friction coefficient, and then if I wanted to find theta, all I need to do is take the inverse tangent. Now, do you see how simple this equation is? And we got to it by doing some really complicated stuff, but only substituting at the very end. So a couple of things that we need to take from here. Lesson number 1 is when you have this, the first thing that you do is you take the body and figure out which forces are acting on it. There were 3: reaction force, weight, and force of friction. The second thing you do is you take components. You take the components along the two directions that you are considering, x and y in this case. Once you take the components, then all you need to do is just figure out which parts are moving, which parts are not moving. If we're talking about something that's static, then we know that all the forces have to cancel out. So this has to be equal to this has to be equal to this. Do not replace any numbers until the end, and then at the very end, you get the most beautiful result ever. I mean, this is beautiful. Right, so that's it for today. This is what you should have understood. The first idea is that when there's no net force, then the body is moving at a constant speed in a straight line, and vice versa. This goes both ways. Second is that if a body A does a force to the body B, then B is doing the same, an opposite force on A. And remember, these two forces are on different bodies. And the third is that the normal reaction force is the force that the ground does to oppose the push of the body on it, which means that it's not equal to the weight. It's equal to whatever push that body is doing on the ground. We will practice this in class a lot because I want to make sure that one thing is, yeah, of course you can state all this, but actually seeing it in action can give some profoundly counterintuitive results. And the job for the rest of this week is for you to be so comfortable with this that you can just see it in your head. Okay, good luck with this, and I'll see you in class.